Now, what was the last topic of electrostatics?
So we have dis-
Yes, am I audible?
Sir, yes, sir. Sir, we are discussing about
Yes, what was? Yes,
Gauss law.
discussing
We
about
need to
what?
discuss Gauss law, sir.
Gauss law. Okay, fine. Gauss law in electrostatics. See, what is Gauss law? Gauss law is a very simple law. It states that flux, whatever the flux is, that flux is directly proportional to the charge enclosed by a surface. Charge must be fully enclosed by a surface. The net charge which is enclosed by a surface, that net charge will be what? Will be directly proportional to the flux which is emitting out of those charges. Okay. It means if a flux is given and then charge enclosed inside the Gaussian surface, what it will be? Charge inside the Gaussian surface will be epsilon naught multiplied by phi. That will be the charge enclosed. Are you getting it? What is happening here? Charge is
Yes.
directly proportional to flux, or we can say flux is directly proportional to charge. The law states that flux is proportional to charge, or we can write flux is directly equal to charge enclosed divided by epsilon naught. Epsilon naught is what? Permittivity of free space. This is Gauss law. That's it. This is Gauss law. Okay. And earlier we have studied what was the flux earlier. Do you remember what is flux?
Yes, sir. Electric law.
Flux was E dot ds. This was the flux, is it not? E
Yes,
dot
sir. It is.
ds. And here we are concluding flux is Gauss law is saying that flux is charge enclosed divided by epsilon. So this is equal to integration surface integral of E dot ds. Using these two, now we can calculate the electric field. Now we can calculate the electric field. We will take this on that side and we will calculate the electric field now. Okay. So this is Gauss law. Okay. Do you want to write down anything? Or Gauss law is taken down?
Sir, Gauss law copied, sir. Everything copied, sir.
Copy. Okay then. Try solving this example. Flux coming out and entering a closed surface is shown in the figure. Find out the charge enclosed by the surface. How much charge is inside the surface? This charge you must calculate. Okay. Calculate it now. How much charge is there inside the surface? Yes, solving it. What is the answer? Not that much time is required. This question is easy.
Flux coming out and entering a closed surface is shown in figure 20. 60, 60. The 45 E now to consider. Sir, 45 we can say. Option 1 we can say.
Yes, what is it?
Option 1 we can say.
45 epsilon naught is correct answer. Very good.
Yes.
Option 1 is correct. 45 epsilon naught. How? We calculated net flux, and net flux is directly proportional to what? Charge enclosed. So we calculated net flux multiplied by epsilon naught. We will get total charge which is enclosed
But yes.
inside. Okay. Now, with the help of this Gauss law, we can calculate electric field of several other charge, we can say charged bodies, especially of a spherical conductor or a hollow sphere or a cylinder or an infinite line charge. All we can calculate, or even a infinite sheet of charge, all we can calculate with the help of this Gauss law. How? See, now let us assume that there is a spherical conductor having charge small q. We need to find out electric field at a point P. Electric field at a point P, which is at a distance small x from the center of the sphere. Okay. Now, how to calculate the electric field at point P? Now we know that flux is q by epsilon naught. This is with the help of Gauss law. Gauss law says E dot ds is equals to q upon epsilon naught. It means what? E ds cos 0 degree. Why 0 degree? Because area vector is parallel. See this n cap. This n cap is area vector. Area of this surface which is enclosed. Okay. Area vector and electric field. Area vector and electric field. Both are in same direction. Hence, here please remember that this is area vector. This is not simply area. Okay. So electric field at this point is always constant because distance is same. So electric field we took outside. Electric field is equals to integration of ds equal to q by epsilon naught. If you integrate ds, means what? Ds was what? A small area, very small area of the surface. So again it is a sphere ultimately. So its area will be 4 pi r square. So electric field into 4 pi r square equal to q upon epsilon naught, or electric field will be q upon 4 pi x square epsilon naught, or we can write q upon 4 pi epsilon naught x square. This is 1 upon 4 pi epsilon naught. This is k actually. So ultimately we are getting kq by x square. Got it now?
Sir, got it, sir.
Need to take down anything?
Sir, copy it, sir.
Fine. Now next solve this question. Find the electric field due to infinite line charge using Gauss law. Again, this is a small question. Let us see it. What we are doing, infinite line charge is given to us, carrying charge density lambda. Okay. So what we will do, we will take a section L and enclose this section. We will enclose this section by an imaginary cylinder. of length L. When we will do this, the flux will be coming out through this cylinder now. Okay, flux will be coming out like this. So ultimately flux will be charge divided by epsilon naught or E dot ds. Therefore, E dot ds equals to Q by epsilon naught. Again, same thing we are doing. E integration ds equal to charge is what? Charge inside this enclosed wire will be lambda into L. L is this much. So charge on this wire, this dashed region, if you are able to see this region, this one. Okay. So charge on this dashed wire is equal to lambda into L. So lambda L upon epsilon naught, L and L are cancelled out. Ultimately, we are getting 1 upon 4 pi epsilon naught 2 pi by R or 2k lambda by R. This is our answer. Okay, take down this question now fast.
Sir, copied. Sir, copied series.
Taken down? Fine. Now, find out the electric field due to uniformly charged infinite sheet. This is a uniformly charged infinite sheet whose charge density is given to us. Okay. Charge density is sigma coulomb per meter square. Means in 1 meter square, the charge we will get is sigma coulombs. So what we will do here, to find out the electric field, we will consider an imaginary cylindrical Gaussian surface as shown. Imaginary cylindrical Gaussian surface. This cylindrical Gaussian surface is uh, passing through the charge sheet. Okay. Now when we apply Gauss law, what we will have, total flux is equals to Q upon epsilon naught. Total flux is what? E dot ds. This is equal to Q, whatever charge is inside, and divided by epsilon naught. Charge enclosed is sigma into S. S is the area. But in E dot ds, see now, we have two surfaces. One surface is here and another surface is here. Both these surfaces together are together forming 2s. So electric field multiplied by 2s equal to sigma s upon epsilon. Okay. So s and s will cancel out. Ultimately, we are getting sigma upon 2 epsilon. This is the electric field due to a infinite charged metallic sheet. Taken down?
Sir, copied, sir. Sir, copied, sir.
Copied. Now, so this was Gauss law, and from at this point, our first chapter is completed now. Uh, did I send you that PDF which was containing all the questions of electrostatics?
Sir, yes, sir. Sir, no, sir.
Just a minute. No?
Sir, you have not shared, sir. Only two, three files of
Just a minute
electrostatics you
then.
shared, sir. Yes.
Just a minute then. Hmm. Your ID is little. Fine now. I have sent these mails. Okay, please check your mail and all the questions. Oh my god, questions. Did I send questions or not? Yes, assignments also I have sent you. Assignments 1, assignment 2. Fine. Fine. Full electrostatics I have sent to you. Okay.
Yes, sir. Yes.
Please check and tell me that you got it or not.
Sir, still I have not received, sir. Sir, but your network is too poor. I think it will take some time.
See, I have sent, I think, yeah, maybe it will take some time. This is what is happening with these links also. Link for the class.
Today, from just at 2 o'clock, only
Okay,
this
now.
problem started, sir. For from my side, that's it.
Oh, no issues. Yeah, it might be some weather issue or something like that. Okay. Now, our next chapter is electrostatic potential and capacitance. Okay. So, what do you mean by potential? Yes, Hemant. Any idea? Just general idea I'm asking.
So, like, generally, use of potential means in uh, mechanical, so the what amount of work done to. So, we can say the work done to bring a
Amount of
charge
work done
from.
or energy? Potential is what?
So,
Yes, 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 yes. Then what is the difference between potential and potential energy? Can you tell me that?
potential energy.
What is the difference between
So we can
potential
say
and
potential is
potential energy? See,
if you do the work, no,
uh,
sir, against that force, it will get stored, no, sir. That is called potential. We can say, no, sir.
that is potential or potential energy.
So the work done will be stored into form of potential energy. We can say like that.
Yes, but the same is the definition for potential, is it not?
The same as the
See
definition of
now,
potential.
see, let's see first. Till now we have studied about electric field. Till now we have studied about electric field. What is electric field? Electric field is the region where force because of a charge can be experienced by another charge. Okay, means two charges can experience force due to each other. That is called electric field or field region. Now, in this region, if I am bringing a charge, if I am bringing a charge from infinity, means charge was very, very far away, charge was not under influence of any electric field anyhow. So when I am bringing that charge, when I am bringing that charge from infinity to that particular point, what is happening? That charge, I need to do some work. Which kind of work? See, the charge which I am bringing is a test charge, which is positive, and electric field is in opposite direction. Then what will happen? Electric field will oppose the bringing of that charge. Like a spring. When you press the spring, what happens? Spring opposes your movement, but still you continue. You go on to press the spring. So ultimately, what happens? The spring gets compressed, but as soon as you leave your hand, spring will force it out, means force itself out completely, and will gain its original position back. Okay, so what is happening here? Potential energy was getting stored inside a spring. Similarly, here also, potential energy is getting stored inside the charge. If I am bringing a charge, potential energy is getting stored inside that charge. Got it now till this point?
Sir, sir, why
Now I am
always?
saying if I am bringing unit positive charge, means 1 coulomb charge. Yes, why always what?
Sir, generally, why every time we are defining every definition by taking only positive charge? Why can't we take negative charge also, sir?
See, because no, we can take negative charge, but then we need to specify the directions. We need to specify the directions. See what happens. What happens? Let us assume that this is the electric field. This is the direction of electric field. Now, which charge will you bring? Can you bring a negative charge here? No. A negative charge is automatically going to come here. Why? Because electric field originates from positive towards negative. And if it is negative charge, electric field will attract it. It means what? Force on negative charge is in the opposite to the direction of electric field. Means charge will automatically go on this side. You need not to bring the charge. Charge will bring you. So what is the work that you are doing? Are you doing any work? No. So who is doing work?
No, sir.
Charge itself is doing work. This is called negative work. Got it? This is negative work. When you are doing negative work, that negative work will be stored in this charge. Means if you bring the charge at this point and when you leave the charge will not go on this side. Charge will not go on the right hand side, but it will go on this side again. Okay, when you leave the charge. So what is happening here? Charge is automatically moving. So our definition of potential is work done by external force which is getting stored inside the charge. What is it? Our definition is work done by external force. So here external force is doing negative work. Generally we define the things with positive work. That's why we take positive test charge. That's it. We always take positive test charge just because of our experimental reasons. So
So
that
how
we
can
can
it
explain
has negative
easily
work,
all
sir?
the terms and terminologies related with that particular. Because see, let me
So
explain it.
because
Okay.
here displacement and the force are in the same direction, no, sir. You can say. Attractive force and
Uh,
displacement and
no, no,
it's
no,
the
no.
same direction.
This
We
is
can say it's a
not
positive work,
about
no, sir.
force. This is not about force. Yeah, with respect to force, but which kind of force? Electrostatic force, not external force. In our definition, we are defining it to be work done by external agent, not by the electrostatic force. Work done by the external agent is our definition. This is our definition. See now, the potential due to some source, see, leave it. This is the electric field. Okay, and this is the electron. Now we are bringing this electron up to this point, and we are bringing a positive charge positive charge to the same point. Okay, now in which case I have to do some work in bringing positive charge or negative charge? Can you tell me?
So to bring a positive charge, you need to do external work. We can say, no, sir.
We need to do external work because of positive test charge.
Yes, sir, because of
Okay,
positive charge, sir.
so when, yes. So when I will, because it is what, it is like a spring. When you press the spring and when you leave the charge, it will go on that side. But if I am bringing the charge from here infinity and I'm taking it at this point, and when I'm leaving it, it is not coming back. This charge is not coming back. Instead, it will go on this side. Why? It is negative now. Negative charge will always go in the direction opposite to this electric field. Got it?
So got it, sir. Yes.
Negative charge will go inside, will go in the direction opposite to the electric field, whereas the positive charge will be pushed out in the direction of the electric field. So here our definition will become what? Here, what is happening first of all? Whatever work I did, I mean I am the external agent here. Whatever work the external agent is doing, that work is stored as potential energy in the charge. Got it? That work is the external agent. And when this charge which I was bringing, when this charge is 1 coulomb, then the potential energy will be called simply potential. Got it now?
Yes, sir, I get it.
Yes, got it?
Yes, I got it, sir.
Take down the definition now. Potential due to some source charge at a point P is defined as the work done by the external agent. Always remember that. In definition, it is work done by external agent in taking a unit positive charge. Now, why positive charge? Because generally we took the direction of current when the current, electricity, electrostatics were being developed. We took the direction of current to be the direction of positive charge. So everything we have defined is related with the positive charge, but it doesn't make it wrong. Why? Because negative charge is nothing, just opposite to the positive charge. That's it. So if anything positive we know, then it means what? We are automatically knowing anything which is negative. Got it?
Sir, got it, sir.
Take it down.
Sir, copy it, sir. Yes, sir.
Yes, Hemant, are you getting it?
Sir,
Any
copy it,
doubt?
sir. Sir, no doubt. Copy it. Sir, copy it, sir. Yes.
Copy.
Sir, I'm audible, sir. Copy it, sir. Yes.
Fine. Fine. Now, see now, what is happening here? Here,
Sir,
I
copy.
am bringing 1 coulomb of positive charge from infinity to point P, and I am finding out potential at point P. Potential, not potential energy. For potential, I need to bring 1 coulomb of positive charge. I need to bring means external force must bring. Whatever work external force is doing, that work is stored in the charge itself on the account of its position. Its position is changing. This is called potential. But when my charge is not 1 coulomb, when I am bringing any other charge, let us say Q naught, and when I am bringing that charge Q naught, whatever work I will do, that work will be called potential energy. Got the relation? When you are bringing only 1 coulomb charge, then it is called potential. But when you are bringing 100 coulomb charge or 200 or 200, 211 or anything like that, then the potential is what? Then the potential energy is called potential only. Potential is for unit positive charge, 1 coulomb of positive charge, whereas potential energy can be of any other charge. Okay.
Yes, sir.
Now,
Okay,
some
sir.
important points are there. If W infinity to P is the work required, see the second point, in moving a charge Q naught from infinity to point P, then the electric potential at point P. Now, this is the same thing which I just said. If W is the work required in moving a charge Q naught, here my charge is not 1 unit, here my charge is Q naught. If I am bringing that Q naught charge from infinity to the electric to that particular point, then the electric potential will be given by what? Work done by external force divided by the magnitude of charge itself. That will give us work done because of unit positive charge. Means if 10 coulombs are taking this much energy, how much energy 1 coulomb will be taking? You'll divide it by 10 coulombs, you'll get the answer. Okay. Work done by external agent is always opposite of electric field. How? See, in the example we saw here, electric field was trying to oppose the incoming charge, is it not? Yes, Hemant.
Yes, sir. It is trying to oppose us.
But is the charge stopping because of this opposition? No.
So no, sir.
Charge, okay, electric field is not able to stop the charge. It means electric field is applied force, but that force is smaller, smaller than the force by external agent. So what is happening? Yes, what is happening here? Electric field here, it is doing negative work. Electric field was trying to stop, but still the charge is coming. This is called negative work. This is the example of negative work. So always remember that work done by external agent is equal to negative work by electric field because the direction is opposite. Okay, take this point down.
That's it. Sir, copy.
Done? Fine then. Now you can start solving the questions of electric potential from the PDF which I sent you. Okay, Word file. Fine. And
Yes, sir.
also please revise the last chapter. Start solving its questions. Okay. From
Yes,
here we
sir.
shall continue tomorrow. Okay.
Yes, sir. Okay, sir.
Okay. Please do check once again that all the files, those 9 files, you got those files or not. Okay.
Yes, sir. I will
Fine.
check.
Okay then.
Thank
Thank
you,
you.
sir.